in this example, we can apply a similar strategy, which is to notice that when we're choosing u, I'll choose t squared, because when I take its derivative, we get 2t, something simpler. On the other hand, if I take the derivative of e to the t, it would just be e to the t again. So it doesn't necessarily get simpler when I differentiate. So choosing between these two, my choice for u would more likely want to be t squared. So letting u equal to t squared, and then dv will be e to the t dt. And this is an okay choice because e to the t has a very easy antiderivative. Okay, so choosing u equal to t squared, e to the t will be dv. So now let's differentiate to get du. So 2t dt, and v will just be e to the t. Right? Doing the antiderivative of e to the t, I get e to the t. And so our integral now will be uv minus integral of v du. So that'll be t squared e to the t minus the integral of 2t times e to the t. Now looking at this, it looks like we've got something similar where I have a product of two things inside the integral. Although this integral looks a little bit simpler than the one we started with, because now say I factor out this 2, what remains is a factor of t that is 1 degree lower than the original. So just applying this formula, we've managed to reduce the integral to something a little bit simpler. But it looks like we might have to apply the formula one more time here to get it into a form that we can evaluate. So we're going to apply parts again just to this part here. So now imagine we're going to just focus on this part. So I'm going to carry down the rest of it. And we'll apply parts just to this part here. So now for the second iteration of parts, we're going to let u equal to t, taking this part here to be my t, or to be my u, and then this part again will be dv, using the same reasoning that we had before, that when I take the derivative, we get something simpler, and here this has a very easy antiderivative. So applying parts formula just to that integral there. So u times v will be t e to the t minus the integral of v times du will be e to the t dt. So we finally see that the integral that we wind up with here, we can now evaluate very easily. Okay, so let's finish it up with that last integral. So the integral of e to the t will just be e to the t, and here I'll distribute the minus 2. So it'll be plus 2 e to the t. So you see here we actually had to apply the parts formula twice, because each time we applied it, the integral simplified, or got simpler with each application. And so we just applied it enough times for us to be able to reduce it to something that we can evaluate directly. Let's see what would be a good choice in this case. For e to the x times sine x, we might not be able to use our strategy to determine which of these would be a good choice for u. I'd say in either case, neither of these are going to simplify very nicely when we take a derivative. For instance, the derivative of e to the x is just e to the x. It doesn't change, so it doesn't simplify at all. And the derivative of sine x is cosine x, which doesn't necessarily simplify either. It's just another sinusoidal function. So what can we do instead? Well, let's just arbitrarily choose one of these functions to be u and one of these functions to be dv, and then we'll try and stick with that choice. Say, for instance, here I choose u equal to sine x, and I choose dv equal to e to the x. Then the derivative of sine will be cosine, and the antiderivative of e to the x will be e to the x. Okay. And when I apply the parts formula here, so this was my u, no, actually the other way around, right? So I chose this to be my u, and this was my dv. So the uv minus the integral of v du will be sine x times e to the x minus the integral of e to the x times cosine x. And it looks like, again, we wind up with an integral that's kind of in the same form as what we started with, although it's just cosine instead of sine. So I'm going to reapply the rule again, just to this part of the integral. And in this case, I'll stick with the same choice for u and dv. I don't want to change it now because I want to be consistent with how I'm choosing these functions. So I'm going to choose u equal to cosine and dv equal to e to the x, so that du is equal to negative sine x and v is equal to e to the x. So let's see what we wind up with now. So again, just applying the parts formula here to this integral, we have u times v will be e to the x cosine x minus the integral of v times du will be negative e to the x sine x. Here, if I clean this up a little bit, what I notice is actually the integral that we've wound up with here. So I'll distribute the minus sign. I can factor out the minus sign and then distribute this minus sign there, so it stays minus. And the integral that I noticed that we wound up with is exactly the same as the integral that we started with. Now, is that going to be a problem? Well, in this case, actually, it is not going to be a problem. In fact, we can use this to solve for the integral algebraically. In other words, we're going to think of this like an expression that we can isolate in the equation. Right, because essentially now what I've got is this integral here that we started with, is equal to e to the x sine x minus e to the x cosine x minus that integral that we started with. So think of this like a variable that we're trying to isolate in an equation. If I can isolate this integral on one side of the equation, then we've solved for it. So that's exactly what I'll do, is I'll add this integral to both sides of the equation so that I can combine it with the integral over on this side, just like I'm solving an equation. So combining it over here on the left-hand side, I have 2 times the integral of e to the x sine x equals e to the x sine x minus e to the x cosine x. And then finally, to get the integral by itself, I'll divide out the 2. So we'll have, or we'll multiply by a half. So 1/2 e to the x sine x minus e to the x cosine x plus c. There we have it. So the trick that we used here was to notice that after we've applied this integration by parts formula twice, we wound up with the same integral that we started with, and we were able then to isolate that integral on one side of the equation, and hence solving for that integral algebraically. And that gave us a solution for the integral that we were able to coax out of there after two applications of integration by parts.